That is correct, and we are now recording. Thank you.
All right, action camera. So first off, let's do robot news. Robot news. Who has robot news out there? Speak
I'm
up.
sure lots of people. Who was at the robot block party? Show off what you saw and what you did.
Yeah, I was there. It was a lot of fun. I don't think I took some pictures, but they're on my phone. Yeah, it was really good. We saw the spot, we saw a spot and A-1 battling it out with Daniel driving.
We've renamed A-1 to -1.
-1. Okay, good.
Yes, because A-1 is just too hard to say.
Yeah, it is. But yeah, there was great food and ice cream and a nice, really good homebrew robotics tables there. And
Big Orange couldn't make it? Jim?
I flew up, so I didn't take Orange on this. Maybe the next one, if I make it in April. There's another one in April next year, so that's really good.
I see conveyor at the bottom of that picture on the screen now. Ubiquity's conveyor.
Yeah, I talked to him, and I talked to the Dusty Robotics guys. We had a presentation from them not that long ago, right? And they were drawing out R2D2s on the floor with the construction robot there. It was, and then there were remote telepresence bots driving around that you could connect to. And I did a live broadcast to the RSSC RRS club meeting, which was going on at the same time, actually, Saturday morning. So I tried to.
Robotics Society of Southern California and Riverside, isn't it?
Yes, Robotics Society of Southern California and Riverside.
It was during our meeting, so we had a live broadcast. Jim was walking around, and we saw a bunch of you there at the meeting, remotely. So it was fun.
I hope it came out good, because
Great.
Yeah, because I was using LTE there, and they didn't want me to use their Wi-Fi, but yeah, there was a lot of good stuff. I mean, robot arms as well. Paddington was there, and there were talks going on in the corner by many different companies, or different participants, but they didn't list the topics, so I skipped most of that and then sat down for a few, and they were really good. And about things about IMUs and software, dealing with one of them was about that, kind of dealing with this the code for stabilizing your for getting IMU information and stabilizing your robot. But
I see Marco out there.
Marco was driving around. He had both of his swappies. One of them was driving. They had the track. They brought the track inside because they thought it was going to rain, but it didn't actually. It wasn't bad weather. But then they didn't really use the track. They only kind of did some trial training runs, I think, on the track for the next I guess
What do
race.
spots cost now? $75,000?
70,000 about. So yeah, it was. I've never seen it in person. I was quite impressed. It was quite nice to see it in person, and wondering if it would run you over if you got in its way. But they assured me no. It's got safety protocols.
Well, somebody was remote controlling it, weren't they?
Yeah. I mean, but if you got in the way and they didn't see you or something, it would. I wonder if that's a good question.
I was surprised by the sound, had the thumping sound. If I didn't know what it was quite ominous.
Yeah, the floor, I don't know if the floor at that at this venue is kind of thin, but when Spot stepped, you felt it like a few meters away. So like a
And it's
thump.
not really a happy sound. It's
No,
it's, it's a
kind of
robot
like-
dog coming towards you sound.
it's the famous Jurassic Park coffee cup waves forming as it steps, No, it was fun. Great event.
Just as an additional in the Spot, the payload at the top does not come with the standard package. I believe that you pay extra for that. And that is the user payload computer that whoever was driving Spot, I forget his name, had a little, he had a little box that it was controlling Spot.
Dan, there was a little dog there called Robot Mike. What's the deal on that?
Oh, the one that was walking around, it was a quadruped that was walking around. The great thing about that, the guy who was running that, the motors on that are also quasi direct drive motors, which are the same ones that I use on Dash 1, which are basically very low ratio planetary gears with a motor inside. And so they're easily back drivable, and yet you don't have the backlash is zero. So I was pretty impressed with that little guy.
It looked like, I'm going to try to be funny here, a robot chihuahua. There's a joke there somewhere.
we were
Robo-Wawa.
trying to get all three of the walking dog robots together, but Spot had gone and done something else, and so we didn't get to do that. But I'm sure in April we will be able to get all the walking robots, all the little dogs, together. And I was talking to the guy who helps me design the head. We are definitely going to redesign the head because everyone said it looked creepy, and we can't have that. So it was supposed to look cute, but obviously it didn't look cute. So the head's going to be redesigned to fit the Jetson NX board better and allow all of the plugins that I need, that I thought I could do remotely, but as it turns out, in the development phase, you sort of have to have a monitor connected and things like that. So the head is being redesigned actually as we speak. Drawing up ideas.
Talking about the dog's head now, not Karen.
Correct. Karen is basically hung up at the moment. Oh, that's a great picture. So then I posted the video, maybe this one in the chat, so you can see. And then of course the difference here is, Dash 1 is 1/10 the price. So if you really wanted to do limb stuff and you didn't want to spend more than $8,000, this is a better approach.
That's great video.
We had so much fun, and kids loved it. Kids, because they really just fell in love with it. Because I think it's because it has a head and Spot didn't. But they remember the balloon.
Oh yeah,
Yeah.
Karen.
So the Karen balloon. I wish we had a picture, Camp.
There's one
But
out
basically,
there.
is there? Because
Yeah,
because Karen was kind of scary, this big mechanical thing, and everybody just thought it was a ladder or something. Yeah. And then we put a balloon on top of its head with a smiley face, and all the kids loved it. And so we now realize what's really important for your robot is that it has a really cool, happy face to it.
It's got to have personality, Dan.
It's got to have personality.
Oh,
Well,
yeah.
your robots have a lot of personality, Cam.
Well, thank you for that. I think that means people look at it and say, I could do better than that.
No, I don't know. If they could, how come they don't? There
Come
you
on in, the
go.
water's fine.
Yeah,
All right.
exactly.
So probably the other big news items this month were Ross World. Let's see, there's a lot of stuff coming from Nvidia. I'll post a link in the chat. And I guess the other big thing is the TurtleBot 4. That's you get a twofer there. because the TurtleBot 4 is based on iRobot's new Create 3. So let's see, where's the Zoom meeting? Oh, there it is. I'm on it. No, I want to do the chat. Sorry.
You know, Camp, Chris and I were doing an Nvidia sort of a live, you know, in person if you were vaccinated thing, hosting. I'm hosting at my place, or we could even host at Chris's place. But I'm of course I'm putting words into Chris's mouth. But maybe we should sort of focus every now and then on loading the ROS to. They have a container that runs on the Nano and the NX, and I think it would be fun just to sort of go through a couple videos and some live stuff and get people sort of up to date. I'm sure NVIDIA stuff keeps changing left and right, but it would be fun to play with, and love to put it up, you know, create a video of us installing the ROS 2 package and on an NVIDIA board and kind of go into town with it.
The things that they were talking about are they've got some perception modules, image pipeline, I guess, to make it faster. But I put a link on the chat there. And so check that out when you get a chance. Where's that link? Oh, yeah, here, Nvidia AI Perception. I think this is, yeah, this is ROS also. It's all ROS based. And then finally, robot news, I guess it's the Indy Autonomous Challenge. Team Tom, and I don't know the name of the university, won the $1 million prize with a $2 million car, I guess. But they did some kind of time trials, and I think they averaged for 2 laps 135 miles an hour. There was some crashing, so there's a video out there shared on the mailing list that shows the crash. So nobody was hurt. That's a good thing. What other robot news is out there? Anybody? All right, let's go to club news. Club news, next month we're going to have elections, and I think everybody's buying into it. I haven't heard officially from Chris yet. Oh, except Joseph. Joseph's bowing. The toughest, well, I don't know, webmaster gets up there also in terms of being thankless, is the program chair. Okay, so we're going to need a new program chair. Joseph Head is bowing out. He's got a new baby, so his hands are rather full, so literally. But program chair is an interesting position. You're basically on the hook for the presentation every month, so it can be tense in that way. But you also get to, you know, reach out there and find people, subjects that you're interested in, and get them in to do a presentation. You own the presentations. So we'll be looking for a program chair this year. If somebody wants to volunteer, that'd be great. And I'll send out an email on that. That's club news officers. The election is next month. Hello, Tim. Any other robot news? I meant to say club news. Okay. So what I need help with? What do people need help with? Say something.
Oh, when you say club news, do you mean other clubs too? Like
Other clubs, fair enough. Jim, go ahead.
well, we're at the Robot Society of Southern California. We're doing a special event where we're joining an Amazon live computer science virtual tour on I think it's November 4th or coming up. Yeah, it's in the middle. It's on like a noon, unfortunately, during the workday on Thursday the 4th. But if you're interested,
For those of you that don't know, Jim's the president of the RSSC, Robotic Society of Southern California.
yes, should remind people, although this group probably already knows me. So you
You're
could,
notorious. Big orange.
yeah. If you're interested in that or any of our meetings, then please go to our website. I'll paste it in here into the chat.
Put a link where they can sign up for the RSSC mailing list.
Yeah, and the mailing list too. I'll post that. But yeah, we're gonna this virtual Amazon thing is gonna. I've never done one, but we're gonna have a Zoom meeting, and then then I will connect to the Amazon live feed, and it's a live interview or presentation from their from different locations, and then they will give you a chance for Q&A via chat anyway.
So this is basically a tour of the warehouse.
Yeah, so this is they have two different warehouse tours. I've chosen this one. I just found out about the computer science robotics special one. It's aimed at students primarily and educators, but I think we fall into that category.
Did they show the Kiva robots in action and all that kind of stuff?
Yeah, there's some, I've seen a video of it, and they do show some of the Kiva robots in action, and but it's going to vary from show to show, but it should be interesting, and probably better than their generic warehouse presentation, which is also good, but more or less covers from how your package gets from you ordering it all the way to your house, more of a for the general public. But this one is for future Amazon engineers. So anyway, we'll see. We've posted info on that and on
What's
our
the date
mailing.
on that, Jim?
What's that?
What's the date on that?
So that's on Thursday. It's Thursday, November 4th at 12 p.m. It's like lunch hour, 12 to 1, if anybody can make it. If you can make it, then we'll be sending out a Zoom link on our RSSC list, and I'll forward it to the Homebrew Robotics list too.
Very fine. Any more club news? Yeah, anybody need help with anything? Come on now, somebody needs help with something, I'm sure. I need help with traction.
I got an
I've
adrenal.
moved the,
I got an adrenal question I need to answer on.
Shoot, Tim?
I'm having a problem where when I'm first turning the thing on or booting the thing off, some of the pins are going to a state trip stuff that I haven't even got under program control yet. What causes that? Do you know?
Tim, that question wasn't real clear. The audio didn't come through very good. Can you say it again, maybe a little
Hold on.
louder?
So I'm having a problem with some of the coding I'm working on. Basically, due to some of the states and some of the other electronics connected to it, when I upload the program or reset the program, it trips some things before the program even gets to the point where it's controlling anything. And I don't know what's causing that. It's sort of weird. Like my audio player will suddenly play until the program gets control of it and stops. So is there some transition time, or is there something with the pins that they're floating until the program takes control of it?
Is this when you're loading your code into the Arduino?
Or resetting the program, yeah. So
Yeah,
in other words,
typically all those microprocessors, all the pins will be floating inputs until your program sets them as outputs and drives them to a state.
then that it would account why something gets getting tripped when I not even have the program running yet.
If it floats high, and that's what triggers it, yes. So normally you would have pull-ups or pull-downs and all of those lines to put them in a safe state.
Okay, I may have to go through and play with that at some point. What's happening is I've got a player here that if it's if its pin gets moved any which way or whatever before I tell it like stay low or high or for the neutral position, it'll trip the audio track to play it by itself. And it's really weird because it will trip it to play. Then when the program get control and puts something on the pin, it stops it. But it's weird that it would do it before the program's even running.
Can
You'll
You might
just get
also-
Pin 13, because the flashing
I'm not,
light.
no, that's in that, I'm not using pin 13.
Okay.
But
Can
but
you-
again, it does flash too. But again, like I have a pin that controls an audio player to tell the player not to play, and basically, when the program is uploaded or I press the reset button and it resets the whole program, whether before it resets it, why even got to the point where it resetted it back and running the program, the pin, something on the that wire, that pin trips the thing and it starts playing the soundtrack.
And depending on your development board, some development boards, those pins might have another purpose when they're not being
Well,
controlled.
I'm using an Adreno. I'm using
Just an
Adreno.
Uno. Is
Tim?
it?
No, I'm using the Mega 2650.
I just
Jim?
posted a link that has a non-authoritative answer to your question.
Tim, can I suggest that whatever pin normally triggers your audio, let's say it's edge triggered from low to high, for example, and I'm just using this as an example, that you tie a 100K ohm resistor to ground on that pin as a pull down, because as the microprocessor goes into reset, as was mentioned earlier, it's floating. And then, I mean, if you just had a really weak pull down, it might pull it down before the pin is tested or whatever.
Or I can try that right now. I was just having a problem with that. It was driving me nuts actually, because I didn't realize that one pin was that sensitive. All right, go ahead.
Yeah, put your question together in an email also and put it on the mailing list.
Oh, I just thought since everybody was here, they would.
You're not using pin 0 and 1 either, too, right?
No, I'm not using any of the serial pins. 2650's got 64 pins. I don't need to use those two.
Yeah,
All right.
the link that Mike posted in the chat's pretty
Now you
informative.
said 100K. You said.
It depends on how much current you feel that you want to pull when it's not directed into that state.
Yeah.
Ultimately, every resistor you have on the board, when not being driven in that state, will drain power. 100K doesn't drain a lot.
I always use 10.
But of course, the bigger the K.
10K.
you
Okay,
use,
I've got
Yeah,
either
well,
one of those. I can play around
yeah,
with it.
the bottom line is this, for those that don't really get it: the bigger the K you use, the longer it's going to take to reach that state. And so, because it's the size of the pipe that the water's draining, and so if you want 10K, it'll happen faster.
Yeah.
I
No,
would use
I don't care on that.
largest.
I don't
The
care on
bottom
that.
li- Yeah, the bottom line is use the largest resistor you can and still get the performance that you want.
All right, I'll start with 100K and see how that works.
Yeah, and then try the 10K, so whatever.
Post to
All
the
right, thanks,
mailing list,
Dilbert.
Tim. Post to the mailing
I do
list.
the
let us know how
opposite.
it
Start
comes
with the 10K first, because recommended is 10K, which still doesn't draw a lot of current, but that's
All
what
right,
you
well,
need.
I can go either way. It's not a big deal. I just was trying, I'm gonna have to do something here at some point.
All right.
Okay,
I'll second the 10K.
Yeah.
The research
right.
I had says that's typical.
all right.
All right.
Thanks,
Who else has a question? Questions I need help with. All right. So let's move on to the main order of business here, our presentation. Bayesian
Show and tell?
recognition. I'm sorry, what? Oh,
You gonna
show and
miss show
tell.
and tell?
Yeah, there. The best part of the show and tell. Who has a show and tell? I do.
I got one.
Oh, go ahead, Jim.
Mine is a video, facial recognition tests I did not that long ago.
That's cool.
And I think, yeah, some of you might have seen it already. If you're
Well, another thing that's happened also on my project here, last night I got it to be able to control the player with the controller, and thus be able to synchronize an audio sound with what I'm doing. And I'm going to be going out to the company I doing this for next week, so they want to see it.
oh, good. That
That's good.
sounds
That's your living room there, Jim?
But this is an office. I have a TV in the office too, but this is where this is the robot room and office. So here's a demonstration using the famous Luxonis Oak D stereo AI camera for facial recognition and integrated into Orange with the voice commands. So here, take a listen. Hi. Orange, hi.
Hello there. I don't believe we have met before. Try telling me your name.
Orange, my name is Jim.
Hello, Jim. It's nice to meet you. Wait while I try to commit your face to memory. Please, only you. Okay. Next time try saying, Orange, hello, to check my memory.
Orange, hello.
Hello there. Jim, it's nice to see you again.
Nice to see you.
Orange, hello.
Hello there. Evie, it's nice to see you again.
So
That's
this,
really awesome.
yeah,
That's
it's
really awesome, Jim.
oh, thank you. So that uses a just a FYI. Oh, thank you, everybody. That uses, I can only take credit for the integration, and the Luxonis Oak D does all the hard work, and the people that built those models and trained them, obviously. This is a series of 3 models really that are combined. First is recognizing first is identifying or classifying a face. And then there's another one that feeds into a facial orientation to correct the angle of the face. And then that feeds into the third one where it actually matches vectors. It's called arc face, and it computes a bunch. It takes the features of the face and sort of gets some vectors out of that, and then it compares this in a database of existing ones, and it figures out the shortest distance, the closest matching database of these vectors of the facial features, and then it comes up with that as the answer. So that it's pretty cool stuff.
So when I saw the camera move, I mean, was it actually centering the face there or something?
No, yeah, that it's not. It's essentially it's just moving up at this point to a fixed angle so that it can see people better. So when it hears you say something like "I'm Jim," it assumes you're much taller than it. But in the future, I'm going to do some more work with that, like tracking your face and stuff like that.
It gives it a little personality, doesn't it?
Yeah, and this is actually a little bit slower. You might have heard those beeps of the USB going in and out, and that is because it's actually got another model loaded on the camera for identifying objects and all. Its normal YOLO V4 model. And so when you say, so I put in logic to change the model to the facial one when you say hi, and that takes extra time. Eventually, hopefully that'll be gone. So if the Luxonis people help me and what have you. But anyway, thank you.
Hey, Jim, what are
Could
you
you
using for
please
the
post
voice
a link to
recognition?
that?
Yeah, I'm sorry. Let's have Ralph say it.
Yeah, I was asking what are you using to do the actual voice recognition?
Oh, for voice recognition, I've been using the Google Cloud for a long time and I've also I have two different voice solutions. One is local using Windows SAPI through a Python interface. And that one works okay for me, but for other people and just better quality, the Google Cloud one is my sort of go-to. But I'm trying to get offline speech recognition to be more reliable with different solutions, like the CMU Sphinx, for instance. I haven't tried it yet, but.
Thank you very
Yeah,
much,
another
Jim.
one
Who
that-
else has a- Jim?
Well, I just want to make a comment because something that Dan and I experimented with is a product called Pico Voice, which you can use for free. And we got pretty good recognition locally without having to go to the cloud with it. So if you're interested in audio speech recognition, check out Pico Voice.
Yeah, that sounds good. I'm always looking for better ones than the Windows one. And then there's also the CMU Pocket Sphinx is the supposedly it's reasonably good, but Pico, I'll look up Pico. What did you say, Pico Voice?
Yeah, Pico Voice. Is that right, Dan?
That's right, Pico Voice. And I think that as long as you're not a professional business, you get to use it for free.
Oh, okay. That sounds better than, yeah, that sounds pretty good.
Free is good. One of the things that I've had some problems with, and I got the Nvidia speech recognition stuff working, but when I use my microphone in my robot with my audio amplifier and preamp and stuff, the results were really poor. If I plug in a professional microphone, the results are great. But that's great if you're in your car and you know the environment is perfect and quiet and you're talking to the robot. Or Jim, as you know, you're in your living room talking to your robot. But in the real world, especially if you're at an event like Robot Block Party and you try to talk to your dog, there's so much noise going on that that the voice stuff doesn't work. And Chris and I were chatting, you know, on our way up about, well, could we possibly retrain the model with all this din in the background to sort of with our own voices and sort of in order to get a speech command that had a higher probability of recognizing what we were saying. I don't know if anybody else is doing speech recognition, but we'd like to take it offline at some point and maybe have a special interest group discussion on speech recognition.
I think, Dan, that one of the tricks to that might be using a beam forming microphone array that sort of pre-processes and speaker localization. And
somebody had mentioned that to me, that and there's actual hardware you can buy that facilitates that.
Well, I mean,
that's basically what the Alexas and all those have built in multiple
I
microphone arrays, and they do that.
Yeah. Also,
which Nvidia library did you use, Dan?
Boy, I have to go back. It was guy from Dusty at Nvidia, which I don't think is Dusty Robotics, has posted a speech recognition based. It's a sort of a Python based thing based on. I think it's based on Torch and PyTorch stuff. There's a bunch of libraries in there, and I forget which model they were using. And I actually spoke to him about it, and he said, "Well, you got to retrain it on a PC. Retraining it on the robot's going to be difficult." And you know, this is one of those things that maybe our technology isn't really there yet. But for robots that are out in the real world, how are they going to learn to adapt to real world situations if we have to go out and record those, bring them back to the lab, put them on a PC, run through the models and all that? I mean, it just seems, you know, there's got to be a better way.
Yeah. I was gonna, I have a slight information on that issue of noise in the room. I brought the robot to the aquarium of the Pacific to do this, bring a drink to people waiting at a table, real customers, and the thing totally failed to hear me. And it only failed after I had tested it before everybody arrived and in the environment where it was going to work, but without the music and without the chatter. So I got it home and I realized in the library I even am using, there's a thing called energy threshold, which you can set to a particular level. And it uses a little algorithm there that will sample the the microphone coming in and make that and then set a level of the ambient noise. And so now my robot after the event is now I tested this and you can find YouTube recordings of crowds and dinner people, wherever. And so every time my robot boots up now, it says, stay quiet, I'm gonna sample the environment. And so then it sets that threshold. And then you can give it commands and it hears you over it because it will not. So that's at least something.
Oh, well, in the earlier days of some of the other robotic societies I was with, they were experimenting with some hardware that will actually adjust itself depending on what it's hearing in left or right ear to do exactly what you do, but it was all hardware. And then it had in the circuitry a gain things to turn the gain up or down to make it so it was stable enough to be recognized. And that was done years ago. I think one of these Seattle robotic groups.
Yeah, this is not something new.
Yeah, so
that does the voice recognition on the phone, but of course you need the cloud to do the Google Voice over the phone. Or actually it's worked on a web interface going up to Google Voice, but you need good internet. And then also if you use the phone, you can use one of the earpieces that really is doing the bone conduction. So it's isolated from crowd noise and only hears your voice. But again, in a noisy environment, it's just voice control with a moving robot in a crowd is just too scary.
Yeah, that's really hard when the robot's moving and the microphone's on the robot. But next time I'll do a demonstration because I put in a few hours into making this, using this feature of energy threshold. Anyway, and it seems to work reasonably well. But if the noise level changes, say from quiet to loud, then you need to redo that procedure. And then, it's kind of a pain. I tried their automatic level and that doesn't work well. I mean, this is free software, so you get what you pay for, but an automatic noise level adjuster would be ideal.
Hey, Jim, why don't you put together an email for that on the mailing list and recollect the thoughts and stuff.
Yeah, that's great. We'll try to do
Again, Jim, when I used to work at Chuck E. Cheese Pieces of Time Theater, they had a microphone in the room there that would adjust the audio amplifier to how much noise in the room is. So therefore, if the room got louder, the main amplifier turned up to compensate for it. But it did have some hardware in on the cars that read it, sampled the sound in the room.
Right, that's sort of the opposite of this. This is like, I need to hear you, so I have to ignore anything below a certain threshold, because the problem I was getting is it thinks you're talking all the time because the noise level's triggering the recognition. And it needs to say,
you need to have either some way of
all right,
software.
let's cover this on the mailing list.
Yeah, we have to move on. Anyway, thank you.
Sorry.
Yeah, thank you. All right, Alan, you've got something for show and tell, right? Hello, Alan.
Alan, I think you're muted.
Sorry. So Camp, this is the conveyor belt commercial. Is that okay? Because it's commercial.
You got to pay $10, man.
All right, then I can show the non-commercial.
No, I'm joking. Show it to us, please.
All right, so let me share.
I'll pay the $10.
Okay, I don't know if you get the sound on it, but here we go. Okay, so we're not getting the sound, but hopefully you can see everything. So actually it's just playing music. So what we have here is a Magni with a superstructure, which is aluminum. Also has a LiDAR on it, and it's a Raspberry Pi, the Raspberry Pi touchscreen. We're using these fiducial markers, and originally we called this project Breadcrumb because the markers are both directional and instructional. So the red one is a stop marker, and the idea is to automate a conveyor belt. So Ubiquity Robotics, the Magni base, has always been a development platform, and most people we try to explain what a development platform, they don't get it, especially software people, and say, oh, we'll do everything in simulation. But we were up at Robot Block Party and say, yeah, here's the basic development platform, and this is what we did with it. And now we have a small warehouse.
So basically, when it ran over and read those tags, it told where it was and what to turn left, turn right, whatever.
Yeah, and the idea is you don't even need everything is done. It's a touch screen programmable, so you don't even need to get in with a, you don't need another computer. You don't need to SSH into it. The idea is it's for non-programmers, non-experts to be able to get up quickly. This guy also has has obstacle avoidance with a LiDAR. Right now, the LiDAR on it is kind of $1,000 LiDAR, but I just looked at the little InnoMaker LDO6, which is $120, and that works almost as well. So we may offer it with, so right now a Magni by itself is $2,000. The tower is another $2,000 and the LiDAR. So the robot as seen is a $5,000 warehouse robot for small warehouses. So, and we're doing some other things. We're partnering with a wireless charging company, and those tests have been successful. And then the other thing we're working with is something called EasyMap, and I'll talk about that but that uses LiDAR. It's a different way of doing SLAM and making.
Didn't Mark Johnson do a presentation on that 3 or 4 months ago?
Yeah, so yeah, that's working too. But I don't.
Yeah, that presentation should still be online in our YouTube channel.
Yep, and that's working too. And the thing is now I'm really impressed. I got this little, and I guess.
Speaking to your mic, dude.
I guess Mike Wimble has been using these little LDO6 LiDARs, which are $120 now, and are pretty awesome as far as I'm concerned. Any LiDAR that I can get working one day is awesome as far as I'm concerned.
Very good. Thank you very much.
That's it.
All right. Well, I got something I'm cobbling together, another skeleton for Halloween. It is Halloween after all. Believe it or not, I went all over town. All the skeletons are sold out. Nobody has any skeletons, but I'll glue some sticks and maybe make a ghost or something. This guy's moving as you get closer. Got some ultrasonics there, and so I'll set it up with a.
What do you got using? What are you controlling it with?
No, it's just Arduino Uno with 4 servos. I'll have 2 servos for the arms, 2 servos for the thighs, and I have to have something to make some noise too, so that when the kids get close for the candy, the skeleton springs to life, spring the trap on them, so to speak.
Is it going to talk?
No, just go boo or hoo or something like that. Again, you're walking up to what you think is just a plain old skeleton, but when you get, 4 meters, 3 or 4 meters away, it starts dancing and
those are pretty. Those are pretty big servos. Yeah. I'm sorry. Those are pretty large servos.
Yeah, they're standard servos. They'll last for a while. Yeah, it'll last through the holiday anyway. That's it. Who else has a show and tell?
Cap,
Come
I
on,
can
any
show
more?
people
what an LDR06 looks like. If you, I'll just hold it up to my camera. I don't know if you can.
Those are like
can-
$130, aren't they?
Yeah, they're pretty nice. They're really small, and you know, you can hook up to them with USB if you want. So
That's awesome.
So
Who
that's
else
it.
has a show and tell? Going once, going twice? All right, let's get to the main event here. That would be Bayesian recognition by Chris Mayer. This is part 2 of his talk on AI. To give a quick recap and then move on to Bayesian recognition. And this is leading to a third finale of the trilogy, right, Chris? That'll go on into neural networks. Without any further ado, Chris Mayer, ladies and gentlemen.
All right. Thank you, Camp. Yes, my name is Chris Mayer, and I volunteered to be the guy that they call when we don't get another speaker. So I'm going to quickly segue into Camp's plea. We do need the Sergeant at Arms, or no, what was the title, Camp? Joseph Hetty is stepping down.
For a
Program chair. Yeah, so we do need a program chair. Joseph Hetty is stepping down, so we do need someone to fulfill that role. It's an easy role, so if you've been enjoying HBRC, please consider stepping up and becoming one of the officers. And another side about that is if there's a different role you would like to play, most of the officer positions are pretty fluid. So if you wanted to do a different role, one of the other officers can slide in. I've been the president, I've been the secretary, I've been the treasurer, and I'm currently the sergeant at arms. So I'm willing to fill in wherever there's a need. And I'm flexible. So if anybody wants to be an officer,
Don't
please
listen to him. It's an incredibly hard position.
Yes.
For
And
the
as I
record,
said,
for the record, Chris Mayer is a righteous dude.
Thank you, Camp. So as I said, I'm the guy who steps up when they don't have anyone else lined up. And the last time this happened was well over 3 years ago. It was actually in July of 2018. So the first thing that I want to do is give a hearty round of applause to HBRC and the officers, because they keep getting quality presentations every month. And it's only every 3 years that I need to step in because they can't get anybody or someone cancels at the last minute. So that presentation, really quickly, I'm going to share my screen. Yes, I should. I'm a host. I should be able to share my screen. So that talk, part 1, is available on YouTube. So if you missed it, please go and watch it. It's a really good talk about AI in general. And I focused on mostly evolution algorithms, genetic algorithms. So let me pop that up. Also, as I'm giving this talk, feel free to interrupt and ask any questions that come into your mind. I prefer an interactive discussion rather than a dry lecture. So if anything I say doesn't make sense or you need another example, please just pipe up and ask. You can either talk out loud or type something into the chat messages. And from time to time, I'll glance to see if there's any questions if I'm losing anybody. Hopefully I won't be. All right, so let's get into a quick outline. As Camp said, I'm going to start off with a quick recap of the last talk that I gave 3 years ago. Oh, one thing I wanted to mention on the YouTube channel, for some reason, they broke it up into 6 10-minute segments instead of a single 1-hour video. So start with part 1 and then find parts 2 through 6. Actually, I have a link, and let me post that in the chat right now.
I was going to suggest to someone add that to a playlist, because I found them, but they weren't all in a single playlist, so I had to add it to my queue separately. I mean, I think somebody could make a playlist on the HBRC.
That's a great idea. I just posted a link to a Google Drive, and that's so that everybody can get a copy of all the JPEGs and the videos that I'm going to present tonight, as well as some HTML pages that I'm going to reference, and also some source code to a live demo that I'm going to show at the end of this talk. I will post the link again at the end of the talk because it'll probably scroll up and get lost in all the chatter. So yeah, we're going to start off with a quick recap. Then I'm going to jump into Bayesian recognition or Bayesian classification. Similar, but there's a subtle distinction that I'll get into. I'll start with a very simple example, and I'm going to go from start to finish of how the Bayesian system gets put together and used, because I want you to get the easy explanation first, and then I'll go back into more detail and get some finer points on how to set that up. And then I'll finish by showing you a real live example. It's actually something that I coded up just a few hours ago. It was like 3 o'clock in the afternoon. So just a few hours ago, because I came up with an idea. This is a great, simple thing that I could give to everybody, and they can play with this stuff at home. And we'll go through that so everybody understands it. So the goal is for everybody here to be able to do a Bayesian recognition system on their own at home, modifying the source code I give you, or understand it well enough that you can write something from scratch. Because I'm all about homebrew. You guys should all go be playing with this stuff at home. So let me pull up. I'm going to share screen. Okay, can you guys all see that? I will assume that you can.
We can see it, yep.
Okay. Usually one of the first questions that people ask is, what is the difference between AI and ML, artificial intelligence and machine learning? And if you Google that, you're going to get 1,000 different answers. And I don't really like any of them, and most people don't like any of them either. The simple one that I tell everybody is artificial intelligence is just something that behaves intelligently. And it doesn't really need to learn anything. Machine learning is in the name, it's learning something, so it's going to get better and better as it does something the way a human does. A good example of AI on the low end, a simple PID loop would be considered AI. It doesn't learn, but it does something intelligent. It gets the current state, the current momentum or velocity, and it knows what to do to get to a certain goal state. And my next button is hidden. Another example would be like chess or checkers. Any 2-player zero-sum game, Tic-Tac-Toe, Connect 4, would be considered AI if it's not going to learn. Now, algorithms like minimax, alpha beta pruning, there's killer move heuristics, there's all kinds of cool algorithms that people have applied to checkers and chess. And the end result is we get a really good game out of it. It makes some really good moves, but there's no learning involved. In the same situation, there's a good chance it's going to make the same move as it calculated this is the best move. When you add learning to the mix, it might make a different move, especially if it tries one path and it gets the pan speed off of it, and it's going to learn, well, I'm not going to do that again. Let me try something else. Other examples that I showed last time, if you remember, was Menace. And this was a simple matchbox learning tic-tac-toe computer. And this would be considered an example of machine learning because this actually learns how to play tic-tac-toe. You look at the current state of the game and you pull out a colored bead that represents what the computer's next move is going to be, and you play a game. When it wins, you reinforce it by adding a bead of that same color into the matchbox, or you can add 2 or 3. And if it loses, you remove that bead. So over time, it's going to learn how to play tic-tac-toe. Now, even though this is an example of machine learning, this is not very practical. The reason is because the solution requires an exhaustive brute force search of the entire solution space before you can come up with the optimal answer of, or the optimal algorithm of playing tic-tac-toe. It has to learn what to do in every single situation. Completely impractical to use that method for something like chess or checkers. Now, the ML method that I focused on mostly last talk was using genetic algorithms. And just a quick review of what that is, you start with a population of agents, and then you evaluate them with a fitness function. Selection is usually just taking the top n. Like if you have a population of 100 and you want to take the top 10, and then from those 10, using mutation crossover functions, you make a variation of those 10, generate 90 more, and repeat, rinse and repeat, and eventually the system is going to learn whatever it is you're trying to learn. That's a general idea what a genetic algorithm is. The examples that I showed, 2 of them, one of them was our robot Mini Watson, which is a mini version of the Big Watson. And the idea here is we wanted to have this computer, this robot, learn how to walk by itself autonomously. The reason we built Mini Watson is because every time Big Watson would fall, you're talking hundreds of dollars of potential repair, and Mini Watson with standard servos is going to be much more cheap to fix when he falls down and goes boom. This is another robot that also learned how to walk. You can build this for less than 10 bucks. This is just SG90 servos and popsicle sticks and some 3D printed brackets.
We're only seeing the slides. Are you trying to show robots?
Are you seeing a picture of a blue robot?
No.
Oh, you're not seeing anything.
See your word pad.
We're still seeing your first slide.
Oh. Thank you for letting me know. Let me stop share. Share. Oh, I see. I thought it was sharing a window. It's actually sharing a screen. Now, is that better?
We saw it for a second and then it went away.
Oh, you
It
just
looks like
moved-
we're still
There
seeing
it
the
is.
screen.
That's
There's a
where
window.
we're seeing a particular screen.
Yeah, we're looking at a screen, not a window.
Okay, I'm going to share and try to share the right screen.
The right window.
The right
I think he
window.
wants to share a different desktop screen. Yeah, so
Yeah, I
you're,
do. This is
you're on the other one still.
okay.
It may
I
not
don't
be
know.
able
We're
to,
we're having technical difficulties here. I don't know how to share my screen.
it may not be able to share the second screen of a 2 screens connector. I don't know. I haven't really done that.
I'm sure there's 2 options.
Can you bring the window over to the screen that's being shown?
Yeah, or flip
what I
your two
tried to
screens.
do.
There you go. Now you got it.
That's just, yeah, that's fine.
Okay, I'll switch my two screens. That'll be easier. Okay, let me quickly go back through my slides then. Really quickly, AI versus ML. Checkers, Menace, genetic algorithm. Okay, so this is Watson, Mini Watson. And this was the guy that learned how to walk by himself. And this is a mini Watson that you can build with $10. That it just uses an Arduino. And you don't need a lot of CPU power to do genetic algorithms. This is an Arduino Nano. And that's the beauty of this. You can do machine learning at home on an Arduino with only 2K of memory. So let me show you. Are you now seeing a model of Mini Watson?
Yes.
Okay. This was a video that I've showed before. And as I said, if Watson falls down and goes boom, it's a lot of money. Mini Watson falls down and goes boom, it's a little bit of money. You do it in a simulator and it's free. So we get him to learn in the simulator first, and then we take that data and then we move it over into the real robot. Once it works on the real robot, Mini Watson first, then we move it to Big Watson, and Watson learned how to walk. So you can see he starts off not knowing very much. He'll try to take a step and he'll fall down, but he'll accidentally take a step, and even though he's going sideways, he did move. And then he's going to try to modify that and slowly get better and better. Now, the feature that we're trying to learn here is we want to move in the X and Y direction. So we want to increase delta X, delta Y. But you die when your Z value goes to less than half of what you started. So in other words, move in any direction from your original starting point, but don't fall down. And that's how I defined walking. I'm going to zip ahead because most of the people have seen this video. But by the end, he really quickly learns how to walk. He's mostly sliding on the floor because I didn't set the friction properly in the VREP simulator. But I think he gets up to about 7 steps and slowly falls down. But anyways, that was an example of genetic algorithm for Watson. And I'm going to switch the other stuff to the screen. Now, the star of the show.
What did you use, like reinforced learning in there, or what inside told him whether he was successful or failing?
That was just a simple genetic algorithm. And the thing that it was trying to optimize was how many steps can I take? So the gene, if you would, was just a simple keyframed animation. So you'll notice that the model accurately made sure that his left arm was broken because we accidentally broke his left arm. But the thing that we were trying to select for was the number of steps and the distance. So it would take a keyframed animation sequence and play it until it died. In other words, it fell down. And it would score based on how far did I move, how many steps did I take, and how far did I move from the origin.
So the higher score would give it some confidence?
Yes. So if we go back to this, the population in this case was only 2. So we had the robots sequence that was the highest scorer, and then we would mutate it and make a second test animation sequence. then we would evaluate it. We would actually play it on the robot and score it based on how many steps did you take and how far did you move. Selection was simple. Did you do better or not? Of the two population, the previous best and the new test, which one did you like better? Which one scored higher? That one we kept, deleted the other one, mutated, created a new test, and cycled through. And the end result was learning how to walk. Now the star of the show, using the exact same algorithm, was a MottBot, and I wanted to see if a robot could learn how to do the tabletop challenge autonomously. At first, I wasn't sure it would actually work, but I'll let this run while I talk about what it's doing. It has 4 different states. There's a left sensor and a right sensor. So there's 4 different states based on whether the left and right sensors are on or off the table. And each state sets 3 values. The values are the left and right motor speed and a duration in milliseconds. So in other words, in this state, I'm going to go this fast with my wheels for this long, and then I'm going to loop. So if it stays in the same state, it'll keep going. But the moment the state changes, it's going to now decide, well, I'm going to do something different with my motor speed and different with the duration, and just keep going. So the score feature on this was a main point of genetic algorithms, is that you get exactly what you train for. And initially, I trained it and told it, don't die. In other words, don't fall off the table. That's the point of the tabletop challenge. And it quickly learned to sit there and do nothing. You put it on the table and it does nothing, which is exactly what I asked it to learn. It doesn't die when it does nothing. So the second iteration, I told it, well, you're going to get more points if you move your motors. And the faster you move your motors, the more points you're going to get. And so I took the absolute value of the speed of the motors in each of the 4 states. And the higher those numbers were, that's what it was. And so it learned, and I think you'll see it eventually, it learned eventually to spin in a circle really, really fast. Because spinning in a circle doesn't die, and the motors move really fast. And so that's what it learns. But that's not the tabletop challenge. The tabletop challenge is you have to go to the edges. So the third iteration, I said, I'm not going to take the absolute value of your motors. I'm going to take only the positive values. Yes, I understand you have to back up when you're in a state where one of your sensors is off the edge. And you can see it sort of had a hiccup there when the left sensor is off the edge, the right sensor is on the table, and it backs up a little bit. But then it goes back to state 1, and drives forward. So it's learning how to spin. You can see it's going faster and faster, and it's learning don't die. So in other words, when I get to states 0, 0, or 0, 1, or 1, 0, I have a potential of falling, so don't do that. I'm going to zip ahead to the end, but you can see it's going a little faster. But towards the end, it learns, yeah, I have the necessary evil of going backwards when I'm off the edge, but now I get to zip to the edge, and I get to score my 255, 255 motor values when I'm on the table. And so it just kind of shows that a simple genetic algorithm, again, this is an Arduino Nano, 16 megahertz, 2K of RAM. And there it is, successfully learning by itself the tabletop challenge.
Now, to get that last stage, I kind of missed it. Or the third phase there. What was the final rules, or that it allowed it to finally get the tabletop challenge?
Oh, the final rules were only taking the forward values of the motors. So all of the 4 states, I would look at the left and right forward motor values and add them up, and that was the score. So it learned to maximize my forward movement in all states, even though it had to sacrifice backing up when it's in the 0-0 state to prevent from falling over. And of course, death scored negative infinity. And if it ended up with both sensors off the table, then it scored a negative infinity, and that aborted the test and went on to the next generation. So by selecting for maximizing forward momentum and don't die, we end up with the tabletop challenge. So the reason I point out the different iterations is because it's very important to be careful how you mathematically define what it is you want it to learn. Because I learned in this example, I had 2 failures because I thought I knew what I wanted it to learn, and it went and did it, and I realized, nope, that's not what I wanted. You did what I said, but not what I meant.
Chris, with the
Yes.
point, and I hate to keep harping on this, but with the point system here, and you're referring to it as generic algorithms, but wouldn't this be reinforced learning if you're giving it points?
Genetic algorithms could be considered a subset of reinforcement learning. Reinforcement learning is a buzzword. There's a lot of different flavors of reinforcement learning. Even neural networks could be considered reinforcement learning because you're always reinforcing the behavior you want. You're shaping it, and it's learning how to do it. So, and you're always reinforcing what's right and punishing or de-enforcing what's wrong. So
I have a question, Chris.
Yeah.
Decades ago, I wrote an article about artificial intelligence for simulated evolution, which is a predecessor to genetic algorithms. The conclusion I had was that it was not able to solve very sophisticated problems. It wasn't a multi-layer learning system. And the second thing was that once you learned something, you had a solver for something, there was no knowledge extraction. So you had a black box that could do something, but you couldn't look in the black box and say, oh, the best way to do this is by, looking for the blackest object and move it toward it. You can't extract any knowledge from it. Is that still true?
That is mostly true for neural networks. They're famous for being opaque and black box. However, with Bayesian systems, with reinforcement learning, with genetic algorithms, you can actually look at the data and know exactly what it's going on there, why it's doing it, what parameters are important, what features are important, and there's no opacity, whatever the right word is, to it. The other thing that you mentioned is true, and that is there's a reason there's a lot of different machine learning algorithms out there. I know everybody, especially new college grads, they want to use neural networks and deep learning because they think that solves all problems. And when you have only a hammer, all of your problems kind of look like a nail. However, that doesn't work. Genetic algorithms, neural networks, Bayesian recognizers, they're different tools in the toolbox of ML and AI, and you have to use the right one for the problem. Otherwise, you're not going to get results. It's going to be difficult, and there are some problems that are too large for some of the different approaches. Genetic algorithms tend to learn a little bit slower than Bayesian or neural networks, but the beauty of them is they don't take oodles and oodles of data, and it doesn't take a huge server farm to figure it out like you do with a neural network. The reason I did this on an Arduino Nano is to prove that. You don't need a lot of training data. You don't need a lot of data crunching. You don't need a lot of CPU power, and you can solve problems. Bayesian is kind of in between. You don't need as much data. You don't need as much CPU power. You need a little bit more than an Arduino, and there's a little bit more math involved. But the main point here is use the right tool for the right problem. That's a great question.
I was going to say supervised learning is is commonly what is done with neural networks, right? Because it's with labeled data as opposed to unsupervised learning or reinforcement learning. It says more like what trial and error, the way humans learn, reinforcement, that it improve upon itself with new situations, trial and error method, versus in supervised is here's a bunch of pictures of cats, learn it, and that kind of thing.
Yeah, that's a good description, Jim. Genetic algorithms, you tell it what you want it to learn, it will learn by itself. Bayesian and neural networks, you have to have them labeled. This is a cat, this is a dog, this is Jim's face, this is, Dan's face. And you have to label it, otherwise it doesn't know what to do. All right, any more questions on the talk 3 years ago?
Chris, I'd like to ask kind of a silly question. So you originally had a penalty for if the robot had to back up. And I could see removing that penalty, but you also didn't give it, or maybe I'm wrong, points for the absolute. Is that correct? Meaning if it ran the whole table backwards, would it get 0 points because backwards motors were not positive? And the reason I bring this up is that if you're doing collision avoidance and you're entering one of the legs of a Y, for example, where you can only go out the base of the Y, but you can't go out the other tip of the Y because of the acute angle, you can back through and go down the other side of the Y, whereas you can't make the turn at the junction. And so that is sort of done a lot in Hollywood when you see the stunt driver driving backwards down the small road in Europe, because they couldn't turn around. And so my question is that, did you consider doing the absolute of the motor turning versus just ignore the direction?
Yeah, that's a good question. I actually tried that, and it learned to spin. It would give the right motor plus 255, and it would give the left motor negative 255, and it would just sit there and spin on the table, which solves the problem. This is as fast as I can go, and I'm not going to die because I'm not really going anywhere.
Well, you just multiply the two together. I mean,
that would work. If I could multiply or just, that would actually work. Multiply the two together.
Right.
Unfortunately, because MontBot only has sensors in the front, it would try to back up and quickly die and fall off the table. So yes, I could have changed it to the the product of the two values, and it would have learned just as quickly.
Well, I guess you need backup cameras.
Yeah, we need backup cameras. All right, so let's move on to Bayesian, which is the next type of machine learning I want to teach you guys about. The history here is back in 1985. The powers that be decided that this AI thing was going to take off and it might be something important. So they started an annual conference to get people to write papers and share info. This is the first annual Artificial Intelligence and Advanced Computer Technology Conference. 1985 was it has nothing to do with the George Orwell, but it was just coincidental. And I was asked to give a presentation on a project that I was working on at the time. At the time, I was working at a company called Stellar Systems. And one of the products that they had was a biometric hand reader. It's called the Identimat 2000. I don't know what happened to the Identimat 1000, but they thought that sounded cooler. And this was biometrics for high security access to government buildings.
What year was this?
Now, this is in the early 80s. So I was working at this company. Now this ID, Identimax 2000, I have to tell you, was all smoke and mirrors. This thing was not accurate at all. It was probably one of those government boondoggles that they spend a lot of money to develop something. It actually sort of worked, but it wasn't very accurate at all. The idea was you put your hand on it and it would scan your fingers along the grooves, and it measured the 4 lengths of your fingers. Now think about that. That's all it measured. 4 integers, and it supposedly could identify who you were. Now this actually was about 95% accurate, which is amazing considered how little data that it's actually gathering. But 95% accurate means 5% inaccurate. So in other words, 1 out of 20 times you run your badge through, put your hand on the machine, and you say, I'm Bob, and it says, no, you're not Bob. I don't recognize you, and you have to try again. It also means if 20 people stole your badge and tried to get in as you, as an imposter, one of them is going to get into the building. Of course, 19 of them will get locked out, but a 5% error rate means 1 out of 20, someone's going to accidentally cross-identify with you. And getting into a government building, you can't have that. So I was hired to improve the accuracy of this system, just using those 4 numbers. And that's when I discovered Bayesian recognition. And no, I say discovered in the sense that I didn't discover it. I discovered it as something new to me, because in doing my research on how to improve accuracy, this is what popped up and made the right sense to use with the data that they were using. They were actually only using 3 of the data points, because they took, of the 4 links, if one of them was out of bounds, they would throw it away. And they would call it a match if 3 out of the 4 measured in between the tolerance levels that were set for any particular person's template. So hired to improve the accuracy of this machine and converted it over to use a simple Bayesian recognition system. And the error rates drastically dropped from 5% down to 0.1%. So it was a 50 times improvement. And that was using the same data, just the 4 lengths. And it's just using the same data in a completely different way, using Bayesian statistics rather than the hardwired 3 out of 4 algorithm that they had in their machine. So what does a Bayesian recognizer do? I know this is labeled Biometric Access Control System, but it's pretty much the same thing. I've actually just pulled pages from the paper that I published in 1985 because I didn't want to redo the block diagrams. But basically, it's a very simple system. You start off, step 1 is the enrollment, and you take a couple of readings so that the machine can get an idea of the mean and standard deviation of the measurements that it's making for you. So the first template that it creates is simply a vector of mean and standard deviation for each of the features that it's trying to measure. So as I said before, you don't need a lot of data to train this system. Unlike a neural net, which needs 1 million pictures of cats and dogs, you can get by with 4, 5, 6 readings, and you get really accurate results. As a matter of fact, adding more and more readings, there's diminishing returns. And after a while, your mean and standard deviation aren't going to move that much when you get your 100th sample versus 99 samples. So in practical use, less than a dozen samples are needed. Now, once you've got your enrollment templates, step 2 is you just go up to the machine and take a reading. It gathers the raw data. Feature extraction process processes the raw data and creates what's called a feature vector. Now, in the example of the Identimat 2000, the features was the raw data, because the raw data was generated by sliding a physical bar with LEDs on it and having a timer and just counting how many timer ticks before the LED saw light peeking around the tips of your fingers. And that was an integer value. It was directly used as the feature. That's not always the case, and we'll talk about that later. Usually you're going to extract some mathematical formula of the raw data to generate your feature vector. Then step 4, you want to match that reading of the features you just extracted, and you want to compare that against the stored template. Now, when we say compare the feature, what we're doing is we're measuring the distance of this reading from the mean of the template in units of the standard deviation of that feature. So I'm going to pause a while for that to sink in and see if there's any questions. Some features are going to have a larger standard deviation than others, and you want it to be in standard units of the standard deviation of the feature, so you can get a statistical measurement of how likely is it that you are who you say you are based on these features.
When you say feature, you're talking about the length of 4 fingers.
Exactly. There's 4 features in this system of the ID 2000, and each of those features represents the length of a finger. So going back to whose question was it? There's no opaque things going on here. You know exactly what the features are, what you're measuring, and how it helps the system. There's no hidden black box stuff here. So then it compares with a template, and it says, are you close enough to the guy you say you are? And then I'm going to give you the results. Now, for the government building, they had these machines in between 2 locked doors, and you would go into one door and it would lock behind you, and you'd put your badge and your hand on this, and if it recognized you, it unlocks the second door and you could get into the building. If it doesn't recognize you, alarms go off and you're in a locked small room and the guards come and get you. So you can do whatever you want with the results. Now, step 6 is actually often omitted and is completely optional. And that is modifying the template. A simple way to do this, for example, if we go back to, oh, I didn't show that slide yet. So we'll stay here. So you can take that new reading, and if it recognizes who you are, it's close enough, it can now take that reading, add it into your enrollment data, and now instead of saying 10 enrollment readings, you now have 11, and it can recompute the mean and standard deviation. The benefit of that is if there's a feature that's going to slowly move in time. For example, your fingers might grow. If you log into the system as a child, you're going to be growing. Or if you're using height and weight as an example, as you gain weight or lose weight, you're going to slowly change. And you can make this so that the enrollment template can be slightly modified based on the most recent uses. You can either add it to make 11 readings, or you can do a moving average and you delete the first one and only use the most recent 10 readings and recompute your template each time it gets used. So that's the simple block diagram of how to use a Bayesian recognition system.
Chris, if your fingernails got longer and then you cut them, would that cause a problem in this particular system?
In this particular system, it didn't, because your fingernails were elevated slightly above the grooves, and it was only looking at the fingers, and once the finger curled up away from the glass, it was using a photo transistor LED pair, and fingernails didn't seem to affect it that much. Oh, and there was another cool innovation they had. They had a temperature sensor. So if you cut off somebody's hand, like you see in the movies, and tried to use the severed hand to get into the system, it was actually using an infrared wavelength, and the absorption of your hand and the blood changes and the temperature changes, and then it would automatically not work. So that was just a binary. Am I going to bother to read this at all? You know, bother to take the 4 readings if the temperature and the IR reflectance doesn't match. So you can do lots of fun, cool things. So let's go over a simple basic example from start to finish. And this is an example with just 2 features. And let's just call it height and weight chart. So we have 3 people enrolled, and I've got 10 dots for each one of them. So they took 10 measurements each. And the circle represents 1 standard deviation out from the enrollment readings that they did. So 10 readings, created the template. That was step 1. Then step 2, now we're going to take a reading and we're going to get a new, can you see the mouse? Or is it just a picture?
No, we see the mouse.
Okay, so say we get a reading where this mouse is right here. And we say, yeah, I'm the red guy, and here's my reading, and then we'll extract the features. Again, the features might not always be the raw data. And we're going to compare it with the template. In this example where my mouse is, it says, yeah, you're the red guy. And on we go. And we either update the template or not as we so choose. And now let's get into some details. So this is the system in its entirety. You can throw as many people as you want into it. You can enroll them, and then you can figure out who they are just based on their height and weight. So next, we're going to get into some details and drill down into what's going on. In this example, we have our 3 classes, and there are some really important things to note here. Now, the first one is some of the readings are outside the standard deviation of the template. Going back, I purposely put a blue dot and a red dot outside to show you that, yes, that's going to happen. I think 1 standard deviation is what, 67%? The second thing to note is some of these readings are actually inside somebody else's standard deviation. This green guy is not quite in there, but I think this red reading right here could potentially be inside the green guy's standard deviation. And that's where we're going to get some of our errors. So that brings up a really important question, and that is, how wide should we allow a match? In other words, how many standard deviations out should we set our tolerance to be? Of course, making it smaller is going to increase the false positives. And making it larger, I'm sorry, I said that backwards. It's going to increase the false negatives. If we're looking 1 standard deviation versus 1/10 of a standard deviation, you can see that we're going to reject you more often. You say you're Alice, but I don't think so. It's going to happen more often. If you make it too wide, let's say if we go 10 standard deviations out, just to be completely insane, and that's going to increase your false positives. Yeah, you say you're Alice, but you're really Bob and you stole Alice's badge. And yep, I agree. You fit within 10 standard deviations of her template. So let's talk about errors. And errors is what we want to minimize. So the 2 types of errors are false positives and false negatives. And the top picture shows an example of I always get these backwards, the false negative. And that is, if you take a reading and it's inside this hashed area, then yeah, we know who you are. But every once in a while, you're going to get a reading in the tails of this Gaussian bell curve, and we're not going to recognize you. You're going to either have to do it again, or you've failed. That's an error. On the other hand, this is 2 people, 1 person trying to impersonate the other. And in this case, person 1 is the person with the template. And so this shaded area represents the area under person 2's curve that can mistakenly be identified as person 1. And that's the second type of error. Now, these two types of errors are at odds with each other. If you turn the tolerance up or down, you're going to get different results. So really quickly, if we talk about tolerance, you get type 1 and type 2 error rates. One comes up while the other goes down. Really quickly, if your tolerance is set to 0, then nobody's going to get through the system. 100% of the time, it's going to say, you're not Bob. However, 100% of the time, it's not going to accidentally let an imposter in. On the other end of the scale, we have, you're probably Bob. And I'll allow that. The problem now is imposters have a higher likelihood of impersonating Bob. And usually these systems are set to what's called the crossover point, where the two errors are the same percentage. Now, you don't always want to do that. And two examples that come to mind, when we were testing this system, we used it in a college lunch line because they were having a problem with people who were paying for the lunches, giving their cards to their roommates or friends to go get free food. And in the lunch line, there's a lot of people streaming through, and you want it to be quick. So you want the type 1 error rate to be really, really low at the expense of, okay, so if your roommate tries to get a free meal, if it's 1 in 5, we don't care. As long as we catch 4 out of 5 is going to be enough to get them to not try it the next time because the embarrassment of getting caught. So in that case, you set the tolerance way to the right. So you want kids to get through and not get rejected as often to keep the line moving at the expense of, okay, so imposters can get through a little bit more easily. And as I mentioned before, in a federal building, you want your tolerance set to like 2 or 4 or something much smaller, because the inconvenience of having to run your badge a second time is nothing compared to an imposter just broke into your federal building. So this shows that you can set the tolerance depending on what you need your system to do. Any questions so far? All right, well, that's error rates in a Bayesian system.
Chris, dumb question. The bell graphs, each one represents the entire hand of different individuals, not fingers.
Oh, this just represents a feature of the individuals.
Okay, but
so
cluster
this is just
1,
a single
2.
feature. Yeah, for example, this could be the pinky finger length of the red guy, the green guy, and the blue guy. This represents a single feature.
Oh, okay. A single feature of
Yeah.
each individual.
Yes. So the next thing to talk about is what makes a good feature. Because some features are good and some features are not good. So let's go back to this picture and really quickly, and I'll point out a few more things. What's good about a feature? Imagine there's a bell curve that takes everybody's data into account. And so you have a larger bell curve that encapsulates the 3 of these bell curves. We want the feature to have a good spread. We want it to be spread far apart. If all of these guys were lined up right on top of each other and their means were too close together, that's not a good thing. So we want the means of the features to be as far apart as possible. Now, the second thing that makes a good feature is to have a high Q, which is basically a small standard deviation. The skinnier these widths are, the better that feature is going to be. So a good metric, if you want to measure which features are better to see which ones you want to use in your system and which ones you can get rid of, if you take the standard deviation of the means, so you take these 3 means and take the standard deviation of them, you want that to be as high as possible. So you put that in the numerator. And then the mean of the standard deviations. In other words, what's the average thickness of each of these bell curves for the individuals? And you want that to be as low as possible. So you can measure a feature by taking the standard deviation of the means and dividing by the mean of the standard deviations. I know that that's almost a tongue twister, but visually what you can see here as an example is it gives you a rough estimate as to how many classes a particular feature can distinguish. In this case, you can roughly tell 3 people apart, or if this was height and weight, we'll call it weight, you've got, or height, you've got short people, you got medium people, and you have extra tall people. And the more buckets that you can distinguish, that's a better feature. Now, of course, we can only tell 3 people here. What happens if you have 100 people enrolled in your system? Well, you're going to have a lot of overlap, which is why we use more than one feature. So with multiple features, let's say we have this feature that can tell 3 buckets, and we have another feature that can separate into 3 buckets. You might expect that the total number of buckets is going to be 9. And as the number of features you add, you might expect that the distinguishing buckets is going to increase exponentially. However, that turns out not to be the case. And the buzzword for that is called correlation. In this example, we have height versus weight, and usually taller people are more heavy. So you can see by just using height, you can get 3 classes, but by adding weight, because the data is highly correlated, adding the weight feature doesn't really give you any more distinguishing power in this system. So we not only need good features that have good distinguishing power, when you're looking at subsets of features, what subgroup to use, you need ones that are not highly correlated. And there's a trade-off between correlation and number of buckets that you can distinguish. I think I have a slide. There's a buzzword. I'm going to jump ahead. Yeah, it's called the Curse of Dimensionality. And this talks to, as the dimensionality of the feature space grows, the number of configurations can grow exponentially. And therefore, the number of configurations covered actually decreases. A good example of this would be the birthday problem. Everybody knows the birthday problem. You have 365 buckets. So any random person can be easily separated into 365 different days. But if I think it's the number's like 29, it's a small, surprisingly small number. If you have 29 people in a room, the 30th person comes in, odds are more than 50% that his birthday is going to match someone who's already in the room. And that's one of the, I guess, side effects of Curse of Dimensionality. As you add more and more features, you're going to actually get to a point where you start to decrease the accuracy of your system. And most of that is just the spread of the probability waves just gets messier when you're adding more and more dimensions. Another thing that's not necessarily mentioned on this slide is as the number of features increase, the need for the enrollment data now also increases. If I have 10 dimensions, 10 features, I'm going to need probably more than 10 readings to get a good standard deviation and mean for all 10 of those dimensions. So the more dimensions you have, the more training data you're going to need. That's another byproduct of trying to get too many features going. So
I'm sorry, could you back up that slide was mainly talking about the number of features, right? And whereas you're also, that's the dimensionality is how many features basically, as opposed to you were also talking about the birthday example, which is, that's one feature, right? But
it's one feature with 365 buckets, but I was trying to point out that really only 30-ish buckets are useful.
I see. So that bigger number, 365, didn't help. It starts to diminish.
It starts to diminish, yeah. And you're right, the number of features is the dimensionality, because you can think of a reading as a single point in, for example, the ID 2000. It's a single measurement, which is a single point in 4-dimensional space. And you're trying to measure how far away from the mean point in 4-dimensional space is this reading. And so if you have 100 features, you're in a 100-dimensional space, and your distance just spreads out. You know, the square root of the sum of the squares, when you'd have 100 of them and you have Gaussian error in each one of them, that error spreads out pretty rapidly.
Which means you need to take more data, more enrollment data, right?
It means two things. You're right. It takes more enrollment data to get a good, stable mean and standard deviation. If you just take 2 readings, for example, and you can compute a mean and a standard deviation from that, but guess what? That's not going to be close to the true mean at all. And so I know there's statistics formulas that tell you how many readings do you actually need, such that if this reading is in the 95 percentile range, which I think is something like 2.7 standard deviations out, can you be 95% confident that that's the right mean and you're really in that interval? Because the mean is just a statistical guess. So I hope that makes sense. So any more questions about number of features, or the errors, or the tolerance? Okay, cool. Now we're going to move on to a little more complicated example, hand geometry. Now the Stellar Systems Identimat 2000 only took 4 data points, but modern hand geometry, if basically you can just look at the shadow of somebody's hand and identify them. And it's actually as accurate as facial recognition. In this picture, let me blow it up. Is that clear enough? There's 23 data points that you would take from a hand, and from this you can get lots and lots of good features. You can get the Euclidean distance from any point to any other point. You can take the Manhattan distance. You can even take triangle perimeters, or you can take triangle areas. Now, useful features would be things like, how big is the hand? What's the total volume? Or obviously, what's the length of the fingers, or the width of the fingers, or the width of the hand itself? Other features could also include the sum of 2 features, or the product, or even the ratio. Ratios of features actually sometimes turn out to be really good. A good example of when a ratio would come in handy is, let's say you have a camera and you want to hold your hand up to it to be recognized. Well, the size of the image in pixels is going to vary depending on how far you are from the camera. So one good idea, if you have a system that you're holding your hand up in space to a robot, is to take the width, for example, from point 1 to point 23, which would be the width of the hand, and divide all the features by that width. So you get an automatic feature that would scale. So for example, the distance from point 1 to point 4, which would represent the length of the little finger, by itself as an absolute number might not be a good feature. But when you divide it as a ratio of the width of the hand, now you have something that might be more meaningful. The problem with these systems, I won't necessarily say it's a problem, But in advance, you cannot know a priori which features are going to give you the most distinguishing power. And in this particular case, if you look at all possible combinations of lengths and perimeters and areas and ratios, you end up with tens of thousands of potential features. And as we saw, we were not going to use tens of thousands of potential features. We only want the best ones. And as we saw, we can pre-rank the features by the standard deviation of the means divided by the mean of the standard deviations. And we could just say, let's take the top 15. But that's not going to be a good idea either, because we don't know the correlation between the features. For example, the width of this finger and the width of that finger are probably going to be highly correlated, so you don't need them both. So what we do instead is a very, very simple algorithm. We find the one feature. We assume that our system only has a single feature. And then we're going to calculate the crossover point based on our training data and our sample data. And we're going to see what the error rate is. And we're going to do that for every feature. So it's an order n algorithm, which isn't too bad. And we score all the features. And we take the best one. This one gives us the least amount of error. And odds are it's probably going to be the one that you pre-ranked, the one that has the largest spread and the tightest standard deviations, because we're not worried about correlation because it's just a single feature. But now we're going to add feature number 2. And so we have to iterate. This is another order n algorithm. Given that we've already picked feature number 1, we're going to add feature number 2. Which of our 10,000 features now gives us the lowest crossover point? So the end result is now we have 2 features. The odds are that they're probably going to be fairly well uncorrelated. And as I said before, we don't really care if they're correlated or not, because if we have a correlated feature with 100 buckets versus an uncorrelated feature with 3 buckets, the correlated feature with 100 buckets might be a much better shot to add to the feature. And one by one, we add the features until we get to this point in the curve. So we add features and our performance is going to go up, 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 up. And eventually we're going to add a feature and we're going to notice we're at the peak, and now we're starting to degrade our performance by adding more features. And at that point, you stop. So now of those 10,000 potential features, you've got your top, it's usually in order of dozens, certainly less than 2 dozen. It depends on the system, but that's the beauty of this algorithm. It doesn't really care. It's just going to get what's the best performance.
Do you consider each one of those
Yes.
numbers a feature? The number that's on the hand.
Yeah, each one of these would be a feature. For example, let's just look at Euclidean distance. We have 23 points. So that's what, 22 squared over 2 Euclidean distances between any point. The distance from 1 to 2, the distance from 1 to 3, the distance from 1 to 4, the distance from 3 to 17.
Okay, I didn't see
So
where the
there's
Instamat. I didn't see where the
roughly
Instamat.
200. I'm sorry?
I didn't see where the Instamat 2000 measured the thumb. I thought it just did the 4 fingers.
The ID 2000 only measured the 4 finger lengths. Yeah, this is what modern hand geometry uses. It basically just uses the shadow of your hand, and it uses a lot more data than the 4 data points. So we've come a long way since the early 80s. And
by the way, I did a
biometric
Google.
recognition.
I did a Google of Instamat 2000, and there's quite a few hits out there.
Yeah, Identimat. Yeah, it's an
Hey,
old
Chris.
dinosaur, but it got the things rolling.
Chris, could you just go back for 1 second? The dimensionality, the number of features that you have, that's basically only based on the type of sensors. Like you have a sensor that's measuring points, for example, on a plane. Is that correct? So adding additional dimensionality given those sensors is, will head you down the curve, diminishing returns. Is that correct? Look, but adding a non-correlated sensor to that would certainly not have anything to do with that curve, right? I mean, if I were to add the amount of light that passed through the skin, for example, as another feature, that's you're just saying the features within that particular sensor group of what it's measuring. Am I correct with that?
Sort of. When you add sensors and add more data, you have the potentially to do much, much better. For example, in comparing this to the Identimat 2000, we've got 23 points of data. So think of this as we have better sensors. We have an image and we can find these points on the hand. Whereas the Identimat only had a linear groove for each of the 4 fingers. So by adding sensor data and making different and more types of measurements, we get a much better system. And so the end result is we can get more features with more data, as you pointed out, probably because it's going to be highly uncorrelated data. For example, if we added skin tone, that would be a feature to add to hand geometry that would be a great feature to add because it doesn't correlate with any of the other data that we have so far. So adding more sensors generally makes the system improve much, much better. And it usually allows for much more number of features in the final system before this curve starts to turn around and bite you. So really good question. More sensors, better accuracy, better system. So in this particular study, we took our tens of thousands of potential features and we did that algorithm where we added the features one by one until we found the curve. And the answer is, for this particular data set that I downloaded, we get 15 features. And it shows here, these are the Euclidean distance and areas of different parts of the hand that were the best subset of features for this particular data set for this system. And this will give you an idea, usually at about a dozen features. Again, it depends on the accuracy of your measurements and what it is you're measuring, how well correlated those measurements are. So the end result is you would put your hand on the light box, it would take a photograph of it, algorithmically determine where points 1 through 23 are as the raw data. Then it would extract these 15 features and then do the comparison to see, are you who you say you are based on the shadow outline of your hand? And that's current hand geometry, and that's how that works. And all Bayesian systems are pretty much going to be the same thing with almost no modification. Take some raw data, extract the features, do a feature subset, and do the comparison. Now, one thing I wanted to show really quickly, first of all, are there any more questions about that? Because I'm going to
I have one more question. So the next question is, is sort of, I don't know. So these particular points for this system were predefined. So your features are based on the distances between these predefined points. If you had an infinite number of points, but then could only save 20 points of that infinite number, would the system then be able to say, these are the most optimal points to save based on, like, our resolution of the whole hand? like, let's suppose you had a 256 by 256 array, but you only wanted to save 20 points within that. And the feature would then, you wouldn't need to predefine the features. It would then just take all of your data. That's where big data would come in to play and say, well, now this big data system might be better because it could define which features give you the least correlation between those features. Is that not correct as far as how big data works? when
If
you have
I
a lot of
understand you
resolution?
correctly, that is mostly correct. And this end result shows exactly that. For example, you'll notice point number 2, point number 3, I think point number 18 and point number 23 never got used. So the
Right.
idea is you come up with an algorithmic generation of a potential feature set. And then once you've done your training and you found these are the 15 features that work, now you can go back and rewrite your feature extraction code. I don't need to extract points 2, 3, 23, and 18 or any other data that I'm not needing. And you are correct. We could have easily, for example, one feature that's not here is how many pixels between, if you drew a line from 1 to 23, how many pixels are inside the outline? We can't do that with this data. But if you wanted to, you could define that as a feature because you have the image data. And the point is you can define the potential features any way you want to. What this system does is once you've defined them, it will tell you what's the best subset of those features.
Right, but it won't give you the best set of features defining, whatever your K number of features that you've decided to use. Is that correct?
No, it will show you these are the best features from the K that you've defined.
Okay.
Now you can always do K plus infinity because there's an infinite number of potential features.
No. What I'm saying is if you had an array here of, 256 across and 256 deep, and you said, I've got 400,000 hands I want to look at, and I want to know which are the best points so that there's no correlation between any two of the images. Could it pick a set of 20 dots and say, these are the best these are your best features for defining different human hands given 400,000 human hands?
Yeah, the short answer is yes, it could, but there's a much better solution for that type of problem, and that would be neural networks, because neural networks would have vision neurons, and it would take into account individual pixels as a feature. Now you could do, if this was an image, like you said, if this was a 256 by 256 image, you could use all of those 256 squared, which would be 16,000, I think, potential features. And it's just an RGB value or a grayscale value. And you could run it through your Bayesian analysis, do the same thing, find the best feature one by one. And it may percolate up that the pixel in the upper left-hand corner is a great discriminator. I doubt that would happen. But it potentially could happen with image data as features itself. So one of the drawbacks of this is that it needs a human to define what the potential feature set is. The segue into neural networks is basically neural networks is a randomized mathematical description of a feature. And it will find the mathematical description of a feature for you. You don't have to predefine one. The drawback is because it's a random mathematical function, it's not going to find, for example, a neural network would never figure out to measure the length of a finger or the volume of a hand, because it's looking at the trees, not the forest. So there are pros and cons to each approach.
I see.
Bayesian is, like I said, doing the template match, doing the optimal feature finding. You can do this all on a Raspberry Pi. You don't need a lot of CPU power. So we're getting late on time, so I want to quickly get to the demo. If there are any questions, feel free to contact me directly. And the quick demo is, I want to tell everybody what my password is. And I wrote a program that you type in your password and it looks at the millisecond timings between your keystrokes. So I wrote a quick program that takes these 20 keystrokes and takes the number of milliseconds between each keystroke, and that's what the feature set is. So I think I have, and this is the result. I decided I was too lazy to do a lot of typing, so I only used 5 readings to enroll. And so what the program does is it tells you how many readings to go, and you type in, "This is my password," ! Enter key. And after the 5 readings, it computes the template, so you can see a vector of 20 features, giving the average number of milliseconds between key presses and the standard deviation of that feature. Now that I've enrolled, I'm going to type my password again. And this is a simple program. Like I said, I just whipped this out a few hours before the lecture because I wanted a simple example that I could hand out. And I type in, "This is my password," and it says the distance from mean is 4.1. And then I got a 4.9 and then a 6.2. So then I asked my girlfriend, "Hey, could you please come in and try to break into my password? And here's the password. I want you to type it in and see if it recognizes you." And when she typed it in, her first try was distance of 106, 236. The third try, she had a typo and hit the backspace key. And I was just using raw keystrokes. I wasn't doing that. So it ended up
what is that, milliseconds or what is that?
milliseconds, yes. So it took her too long, and that's a bad reading. The next time she typed in the password, the distance to the mean was over 2,000. Then she got a 34. The closest was a 19. So, and then a 137. So with just a simple system, 20 features, just typing rhythm, we found that we could easily at least tell me from my girlfriend. And the closest, so we could set the tolerance anywhere between 6 and 19, and it's going to tell us apart. Now, I used all 20 features, which probably not the best idea. As I said before, we have the Curse of Dimensionality at work, and some of these are probably highly correlated. For example, when you have to hold down the caps lock or going for this special exclamation period. If you look at the double S, I'm sure that the double S is probably much faster than all the other ones, like a 145 or 155. So the timing between this S and that S is probably not a good feature to use. But anyways, this is a simple example that I coded up. I have all of the source code and all of the pictures that I've used. I've entered in the chat. Actually, it's still there on Google Drive. So everybody, please take a look, download the code, play with it, and try it out yourself. Just run the code and get someone else in your household to see if they can get your password the way you type it. And it's just a nice, simple example. It's only like 80 lines of code, and it's really easy to read and understand. So that's it. That's Bayesian recognition algorithm.
Really good speech.
Thank you.
Yeah, Chris, really good.
That was awesome.
I think the hardest thing for me to understand is that curse of dimensionality. I'm gonna have to, I just read up on the Wikipedia because I think it seems like it's mainly the more dimensions you have, the more possibility of correlation. I mean, that's what I take the simple, and more correlation means you're gonna start losing efficient performance.
Yeah, that's one of two things. One is, you're right, with more features, there's a higher chance, like the birthday problem, that you're correlated with another feature. The second thing is because there's Gaussian error built into every measurement. When you spread that error over multiple dimensions, you get more into fuzzy quantum measurements rather than, statistically useful ones.
Oh, spreading the, yeah, you've mentioned that a couple times. Spreading the error out seems to be a bad thing.
Very
All
good.
right,
Thank you.
again,
This was
Thank you.
excellent. It's a refresher for a lot of stuff for me, and learned a bunch of new stuff. So thanks.
Thank you very much, Chris. Any more questions? All right.
Sorry, so I'm a little bit confused, like how do you pick, so how does it work to pick the features, like which is like the optimal features you want?
Chris, Chris, I
Chris,
think
you're muted.
Thank you. Can you see the screen here?
Yes.
So the idea is, you understand how we get the tens of thousands of potential features, right?
Yeah.
Okay. So what you do is you go through all those 10,000 features and you score them and see which one gives you the lowest error rate. And for example, let's say that it's this triangle right here between points 1, 22, and 21. And we're going to use the area of that triangle. And let's say that that was the best feature for this data set that distinguished the most number of people. So that feature we pick. So that's our first feature, number 1. And now we go through the 10,000 features again, or I'm sorry, the 9,999 left. And we say, what's the second best feature that when combined with this area gives us the lowest error rate? And let's say it happens to be, here's a distance from point 1 to point 20. And say that's the second best feature. But it's not the second best by itself, it's only the second best in conjunction with this first feature, which we know is the best. And then we just add the features one by one until our error rate stops going lower and lower.
Okay, so we hit like the pick point you show in the other feature, right?
I'm sorry, say that again?
So you hit like the pick, yeah, like the maximum, I said like the optimal performance.
Yeah, so you start with one, and then you keep adding features one by one, and your performance is going to keep going up, 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 up. And in this particular case, when we got to the 16th feature, our performance actually went down. So that's when we stop and we know this is the best subset of 15. Now, it's actually not the best subset of 15. This is just an artificial intelligence algorithm to find a very good subset of 15. If you want to do an exhaustive brute force search, you want to try every possible subset of 15 features, and that's completely impractical.
So that was going to be my question, is you're kind of doing a gradient descent search around a local, hilltop, essentially, but you don't know that that was the best hilltop to start from, right?
You actually do know that this is the best hilltop because you're starting with the highest hill already with a single feature.
Yeah,
So
but
the odds
it's
are
not
you are
obvious.
doing a gradient descent.
It's not obvious to me that starting with that actually produces the best solution. It seems to me it's quite possible that starting with the 25th one in this one example, but then adding in these other features might produce a better result. It's not obvious to me that just because one feature seems to be pretty discriminative, it's not that feature, it's the actual ordering of the features that ultimately is going to result in this thing. And so to me, this just seems to find a local optimum instead of the global optimum. It would require you to do the brute force search that you're saying is very expensive to find the true optimum.
Yes, that is correct. And you can, if you want, you can write a genetic algorithm to find a better subset. So there's lots of things that you can do. The algorithm that I suggested, best first, is well known. There's also a worst last, where you start with the 10,000 and you discard them one by one. That's a lot slower, especially when you're starting with 10,000 features. But most of the research that I've done pretty much shows that this is close to your optimal performance. You're right, there's no mathematical guarantee, but it's a pretty damn good answer.
Yep, sounds great. Thanks. And then can you share the drive link again? I think I missed that.
I'm sorry, I couldn't hear you.
The Google Drive link.
The link is in the chat.
Yeah, I think I've missed it. So yeah, can you share that again?
I'll copy it and paste it again. So it's not too far up.
Yeah.
Yeah.
All right.
All right, so that link should give you the source code to the This Is My Password folder with all the videos and photos, and a couple of useful URLs to illustrate what I was talking about.
Thank you very much, Chris.
Thank you.
This completes another one of our world-class presentations, if I must say so myself. Thank you very much. All right, so this concludes the general meeting of the HPRC, the Homebrew Robotics Club for October. We'll now move into random access, where we'll chit-chat until security comes and kicks us out. Thank you very much. Again, I want to thank Michael Wimble for that presentation yesterday on behavior trees. That was really awesome.
Well, several people stayed awake at the end. That's always a good outcome.
We were entertained. I'll get my servos running here again. Hard to impress, but easily amused.
I also wanted to mention something about what we were talking about earlier, the audio recognition and speech recognition stuff. I had a demo for the block party, but as Dan mentioned, the background noise was so bad that we couldn't get it working. But I wanted to tell everybody what it was. It is actually Arduino based. And it's a simple Arduino shield. If you want, you can hook it up to anything with a serial port. And it's a really easy turnkey voice recognition system. And you can put hundreds of phrases and it will recognize them. And it's speaker independent. It does run a model locally that's fixed based on a database that the people at Ardume created. But if anybody wants to get into really simple speech recognition, I had this up and running on an Arduino in less than 15 minutes. And it's a great intro into voice recognition. And I think the board only costs like, I think it's 80 bucks-ish. But anyways, I just wanted to share that.
A question about Pico Voice. I tried to do a quick scan of the site and came across something that said that if you wanted to train your own model, your models were only good for 30 days, and then you had to retrain them again and so forth. So can you not build a model and then, hard code it into an EEPROM and use it for the next 20 years with this system?
I don't know. I haven't tried that. That's kind of strange to me. I would imagine if they're requiring you to use their servers as the free version, it's like if you want no ads, you got to pay up. But I would imagine you could download the model and use it yourself.
Well,
I don't think that's true. And in the first time that we downloaded it, that was what you're saying was not the case. And then after we played with it, and I think I mentioned this to you, Chris, is that after we played with it, then I went back on the site to train my own model, and it said, you know, it had this 30-day limit thing, and I basically changed gears and went in a different direction with the stuff that Nvidia was offering, because I didn't want to pay for it. I want to train my own model, and I don't want to pay for it. It's my voice, you know.
Do you know what the fee is for Pico Voice?
I don't.
And what is the NVIDIA system that you went to?
So it's a PyTorch based system that uses Pi audio to input, and I guess I'd have to go through all the different libraries to find out exactly what it's using. I kind of feel like Sphinx is a part of it, but Sphinx has been around for 20 some years. So I think it's open source, right? So
So if I key on Pi Audio, I might come up with it.
no, I would look for Jetson speech recognition, and
Okay.
then you'll find it. You know, and if you email me or whatever, I'll look up where I downloaded it from onto my Jetson board, but I forget exactly. But I
can find it.
Yeah. Well, I mean, while I'm doing this, I might be able to actually find the email that Dusty sent me to say, download this. And I had to, in order for me to get it running, I actually had to compile a lot of it on my system. Things just weren't running. And after I hand compiled everything, I didn't hand compile them, you know, I ran the makes and stuff.
Right.
Then I was able to build the system and get it working. You know, and it works great when the microphone's in the exact position and everything, and it's a good mic, but you move around, and as was said earlier, it may just be some parameter that I need to change. But if that parameter can't dynamically change, then that's an issue, because the robot's moving around and it's in different environments, and it's sort of, for speech recognition to work, it needs to be in, you know, to work in all types of environments, just the way our ear works.
Do you know if the problem is automatic gain control or phase noise from reflections and the like?
I have no idea what the issue is. What in order for me to try to figure out what it is, I think what I will do is start doing some recordings. You can use a sound. It runs on, this is obviously running under Linux, so you can use a sound to do recordings, and then you can play them back. So to test your hardware in a specific noisy environment, that's probably the thing to do, and just sort of listen to the file and go, oh yeah, boy, it sounds like junk. And no wonder the system can't figure out what's going on. So, you know, you may have to train the model. And I thought, well, what I really want to do is, I don't really care about speaker independence. Speaker dependence is better, because I'm the one giving command to my robots. I don't want anybody else giving commands to my robot. So I want a speaker dependent voice that works in all types of environments at all kinds of distances from my robot. And obviously to do that, I'm going to have to retrain it given those parameters. My voice, different angles and different environments and different noise levels.
I'm kind of thinking of Henry the Counting Horse. How
yeah. Hey, what's 3 minus 3? The horse said nothing.
I'm thinking of everybody thought he was listening to the voice, and he was actually responding to the pause and the signals and something.
Oh,
Well,
is that what it was? Yeah.
so you can you do your magic demo where people think it's your voice, and actually it's what you're doing with your your index finger while you're saying these things. And that's what it's keying on.
Yeah, well, really what it needs is somebody behind the green curtain listening to your commands, pressing the remote control.
Or somebody on a video feed down in Central America.
Yeah, well, that would work too. I mean, look at all the wasted brain power we have on this planet. Can't I just take somebody's brain, Abby normal brain, and put it inside my robot?
Luker.
Oh, yeah. That was good Halloween placement.
Yes, and if anybody has not seen that movie, now would be a good time to download it.
Just watched it.
Probably one of the best movies ever. Young Frankenstein, in case people are wondering what we're talking about.
Putting on the Ritz.
Putting on the Ritz. So what'd you get from the exchange?
I swear, I'm looking for a skeleton to animate, and I went to.
Did you go to